Good morning, everybody. Sorry for the delay, and welcome to the motion planning lecture number 4. Before I want to get started, let's just do a little bit of organizational things today. As you can see, we try to record today to make it more accessible to additional students that have requested it. Today we tried 2 different methods, and if it works out, we will post it as ESUS or YouTube afterwards. And if it doesn't work out, then it was an experiment. Second thing I wanted to mention is on the organizational side that you should all be able now to access these programming assignments. If you do not have access, please let us know immediately, because you will also need some time to work on it. And we have extended the deadline for the first assignment by 1 week, and I've posted on ESUS all the exact dates on when all the assignments are going to be due. Similarly, I think there was a question about how the exercises work. So it will be always the same thing. The exercises will be posted with the lecture more or less like today. And then you have roughly 1 week. That will be the discussion. On Friday you submit, and then the week after, on about Wednesday, you will get the graded report back, also via ESUS, and we will also post the solutions to the exercises. Any organizational questions from you? Okay, perfect. And let's get started. So we are in motion planning, and we started by giving you some overview about the taxonomy at the very beginning, the first 2 weeks. And then last week, Andreas told you about search-based motion planning, probably from a perspective that at least some of you already know, where you have a graph and then you run Dijkstra's algorithm or A* to search in the graph. And today we want to look at how can that actually apply to robotics, and how can we use these sort of methods and extend them in order to plan for real robotic systems. Okay, so let's first recap how A* works. So first of all, A* has tons of applications. If we use things like Google Maps, then it's probably some sort of it uses it in the background. In computer games it's used, but also for these sort of robot navigations. Okay, so how does it work? So typically you have as input some sort of weighted graph. A graph has vertices and edges. And it's a weighted graph. That means in this case, of each edge, we have some sort of additional number, d, that gives us some cost. Yeah. We are also given the start vertex and the goal vertex, and another function that is known as a heuristic. So this is a function that maps from a vertex to a real number. And typically we assume that the heuristic is admissible, which meant that it should only lower bound the true cost to your goal. And the output of A* is an optimal path in the graph, which means it's a sequence of vertices that you traverse in the graph, where each of the sequences also maps to an edge. That is what this statement here says. Where the first item in the sequence is our start vertex. The last item in our sequence is the goal vertex. And optimal is with respect to the cost, and the cost is just defined as our the sum of the weights along the path in the graph. And so you also learned, including the proof, some of the properties. So A star is complete, which means if a solution indeed exists, it will find it. It is optimal, which we also sometimes term as admissible, which means it will find the lowest cost solution. And the last property is that it's also optimal efficient, which means for a given heuristic, there's no better way of searching the graph than what A star does. Of course, if you have a different heuristic or a better heuristic, that can still improve the performance in practice. And the primary insight of A star is that we use a data structure which is known as a priority queue that orders all of the entries that we have visited by the F function. And the F function is basically the estimated cost to the goal, which is the sum of the cost to come from the start to an intermediate vertex, plus a heuristic, which is a lower bound on the estimate from reaching from that intermediate vertex to the goal. Okay, so that's kind of great, but then if we apply it to robots, which is what we want to look today, we have additional challenges to overcome. So the first challenge is that in practice, of course, we want to react in real time. So we can't just plan once and then hope that we can just execute it, but we need to react to other robots or humans that share the same workspace. And we have to do that rather quickly. The second problem that we typically have is that the examples you have seen run these very simplistic kind of graphs or even grid roads. But in practice, we have these sort of robots that cannot just move from a grid cell to an adjacent grid cell, but that have additional constraints. So we have learned about that at the very beginning, kinodynamic constraints or non-holonomic constraints. And then largely, we can also have lastly, we can have very large robots. So in this example, we have these sort of drilling robots that can move around, but very slowly. But they obviously take away a lot of the physical space in our environment. And so if you think about A star, you typically have these vertices and the edges, and you kind of assume that the robot just occupies a single vertex. But if you have those really gigantic robots, it's not really the case anymore. And we have to rethink how the graph representation can match these kind of robots. Okay, and so today's lecture is really just about trying to figure out how we can address these challenges in practice. And so we first look at some A star variants that still operate on exactly the graphs that we have learned about last week, but add some additional features that are very handy for robots. And so the first thing I want to discuss is known as bounded suboptimal planning. And so what A star does is it produces a solution for a certain planning problem, past planning problem, and it also automatically creates a proof that the solution it found is optimal. But in many cases, we don't care so much about the optimal solution, right? We just prefer maybe to find a solution quicker. And bounded suboptimal planning can do that, but not only it will be suboptimal, where we don't know how good the solution is, but we can have a user-provided value, so this often termed as epsilon, which tells us how close the reported solution can be in the worst case to the optimal solution. So for example, if I set our epsilon to 2, then it's allowed to have a solution that is basically twice as long as a true optimal solution. So in other words, if our optimal solution is C star, then we can report any solution that has cost C, such that the cost C is smaller or equal to epsilon times C star. And then, of course, if you set epsilon to exactly 1.0, you will get back your optimal solution. If you set it to something smaller than 1.0, it doesn't make sense because you will not be able to find such solutions, since C star by definition is the optimal lowest cost. Okay, so how can we do that in practice? And there's many different algorithms. Today, I will just discuss two. The most basic version is known as weighted A star, or also WA star. And it is very much related to the original A star, which means the expansion order stays the same. So we still use our f function, but the way we compute f is now different. So in the original A star algorithm, our f was the sum of the g value, so the cost to come, plus the h value, which is the estimated cost to go. And now we can expand our h value by just multiplying our epsilon value to it, where epsilon is greater than 1, for example, 2. And in practice, it means that we basically end up biasing our search towards states that we believe are closer to the goal. And the belief comes from the user-defined heuristic function. And it turns out that weighted A star, even though it's an extremely simple extension to the original A star algorithm, is actually bounded suboptimal, which means the solution that will return at the end is at most epsilon times the true optimal solution. And in practice, it actually works really well. And people can kind of visualize that as well. So on the right-hand side, we have some example. So on the left, we have our start state. On the right, we have the goal state. And in red, there's this sort of obstacle. And of course, like here, the optimal path is either going above the obstacle or below the obstacle. So in this case, kind of the green line shows us the optimal path going above the obstacle. And the orange part is highlighting all the different states that our algorithm has explored. So if you run regular A star, you get these fairly large areas of exploration, kind of like this ellipsoid before the obstacle. And the reason for that is that A star also has to compute the proof of optimality. So it cannot actually leave this ellipsoid before it has explored everything, because it needs to ensure that the optimal solution does not lie in that initial state. Now, weighted A star, in contrast, is only bounded suboptimal, and because of that, it can very quickly explore the state and needs to explore way fewer states in total. And typically, the number of states that you explore is linearly correlated with the runtime. And so, of course, if you explore fewer states, then your runtime is also much faster. Okay, so that's nice. But one real big disadvantage of weighted A star is that you still rely on this admissible heuristic. And in practice, it actually is extremely difficult to find heuristic functions that are truly admissible. And often people have to use very simple heuristics where they can prove that it's admissible and that are then in practice not really powerful. So the question is, can we also run a bounded suboptimal planning algorithm if we do if we only want to rely on any function, on any kind of inadmissible heuristic. And then we don't have to think about these theoretical proofs of admissibility when we define this. And that is possible with an algorithm that is commonly known as focus search, and sometimes in short also A star epsilon. And so focus search now introduces a second list, you can say, or second set, or also second priority queue. So in A star, we have this open set or open priority queue. And now in focus search, we have an additional priority queue that we just call focal. And the focus search is a true subset of the open set, but it only includes the values that are epsilon from the currently best value in our open set. So in other words, if the open set is a priority queue, the first element is the one that has the lowest f value. Then we multiply this f value by epsilon. And then all the elements that are on the original open sets that have an f value that is at most epsilon times the smallest will be in the focus set. And now we have a set, and we can freely rearrange elements in the set. And so focal is also priority queue, but we can use an arbitrary heuristic function in that case. And the search then becomes more or less identical to A star, but instead of always taking an element from the open list, we now take an element from the focal list. And the only downside is that we always have to keep the focal list updated at the same time as we keep the open list updated, which means we have a little bit more bookkeeping to do compared to regular listing. And at the end, focus search is also epsilon optimal or bounded suboptimal. Okay, so that was maybe very abstract. So let's try to look at a fun little example of how focal search works. So here we have a graph. I think it might be even the same or similar to what you've seen last week. You just want to apply a different algorithm to it. And the goal is, again, that we start from the start state S, we go to the goal state, target state called T, and we have some intermediate states, and the edges have costs associated with them. And then we start exactly like an A star, so we have to kind of keep track of our G values and of our H values. So the G values at the very beginning for the start node will be just 0, and for all the other nodes, it will be infinite. And the heuristic is here just arbitrary. So here's an example for the heuristic function that is admissible. And you can verify that it's admissible by computing the true cost for each state, and then making sure that H is smaller than the truth cost. And then we have the second heuristic function, H2 is called here. And this one, again, is also arbitrary, but it's actually inadmissible. And that is now the new part compared to the last lecture. How can we see that it's inadmissible? Take, for example, the node N2. N2, we can see that the cost to the goal is 4, 3 plus 1, but the value of the heuristic is 100, which is clearly way larger than 4. And so therefore, H2 is inadmissible. And then at the beginning, our open list starts empty, and therefore also focal list will be empty just because the focal list is always a subset. Now, on the very first step of the algorithm in A star, we always add our start node in it, which means our open set now has S, and our focal set also has S. Remember, in our focal set, we always have a subset that has at most epsilon times the cost. Okay, then we do an expand operation. So we look at what neighbors does S have. In our case, it's only N1. We remove the element we have expanded, which was S, and we add all the neighbors. So in this case, it's just N1. And that means we now have a new G value, which is the cost from the start, which is 1. Which also means we can compute technically the F value now. That would be G plus H, which is 3. So open has a value of 3. And then focal list is just one element. Open is one element, which means focal is also one element. Okay, and then the next task is that we need to expand our node N1. N1 now has 2 successors, N3 and N2. And we do the same thing again. We remove N1 from our open list and we add those 2 successor states, which now also means that we get new G values. So G of N2 is a 1 of N1 plus this cost, and G of N3 is the 1 of N1 plus 2 for the edge, which is 3. And now we can compute again the F value, which is the sum of G plus H. So for N2, it would be 2 plus 2 is 4. And for N3, it's 3 plus 1, which is also 4. So now we have in our open list 2 entries. It's a priority queue, but the value is the same. So the ordering between N2 and N3 is arbitrary. In practice, people sometimes move a type-breaking mechanism, but for our simplistic assumption, it could be in any order. And that also means that independent on our epsilon value, our focal list will have the same elements, because the lowest value is 4. We will at least include all the ones that have 4, which is always N2 and N3. Now, one big difference is that the focal list is also a priority queue that is ordered by our H2 function. And so we have to look here, how does our H2 look like? And then for N2, it's 100. And for N3, it's just 1. So our heuristic kind of tells you, oh, N3 seems to be much better than N2. Which also means if we look at this ordered set of the queue, is that N3 now comes definitely before N2 in all cases. Okay. And because of that, we now have to expand N3, because in our focus search, we expand based on the first item in the focal list, not in the open list. So that will be N3. And so N3 has only one successor, which is T, which means we will remove N3 and add this one successor T in the next step. Okay, so we can see that. So in open, we now still have N2 from the previous state, and we also have T. And now we added N4, which means we can compute its T value now, which will be 5, which is just the sum of the path. Actually, we should have probably highlighted T here, which is 5. And 4, we haven't expanded yet. So we actually don't know the cost. But chief of T is 5. Now we can compute again the cost and try to figure out what we want to expand. And now here's the interesting thing is in our focal list, we have to update our focal list again. So we have to look at the F value in open. So open of N2 would be G plus H is 2 plus 2 is 4. And the f value of t is g plus h, 5 plus 0 is 5. So the lowest value of the f value in open is now 4. And now our focal list will include all the elements in open that are epsilon times 4. So if our epsilon is greater than 5 over 4, then we will actually also include t. And in this case, we have t and n2. And now we again have to look at focal list is ordered by h2. So h2 of n2 is 100, h2 of t is 0, which means the best value or the lowest value in the focal list will be t, and it will be first. And that means the next state to expand will actually be t. And then we're basically done, because once we expand the target, we found a solution. And in this case, we have kind of some remaining values in both of our open list and the forecast. Okay, and we found a path in this case, which is 5. Okay, and then I guess the question is, what would actually change here if our epsilon value is smaller than 5 over 4? That slide where I put in the assumptions of what would happen in that case. So we now assume epsilon is, for example, 1.0. How would open and focal look like in that case?
For example, please explain again how big the 5 over 4 mentality.
So that was just an assumption. So basically, the definition of the focal list is that it has all the entries that are at most epsilon times the smallest value of f. So here, the smallest value of f was the f value of n2, and the f value of n2 was 4. So epsilon, let's say if I put 5 fourths times 4, so it makes 5. So then we would include all the elements that have as cost that is at most 5. Yes?
Yeah, so we would explore deeper, we would explore into because it would be started. This one was better over 5.
Exactly. And then it would basically take one more step before we actually expand T. Okay, perfect. Any questions about bounded suboptimal planning, weighted A star or focus search? Okay, no questions, and we can move to the next topic, which is anytime planning. So as I said earlier, one big challenge is that we need to kind of react sometimes to changes in the environment in real time. So often we are not necessarily interested in finding the optimal solution, but we want to find some solution very quickly. And then if we have some more computational time, maybe we can improve that solution a little bit. And whenever we really need that solution, we just take whatever best solution we have found until that computational budget is limited. And so the most basic approach of any time planning is actually based on these bounded suboptimal plans. So we have just seen that if we apply something like focus search, we need to potentially explore fewer states. We had also this visualization in the weighted A star. So it seems kind of logical that, oh, we just start with like a really large epsilon, like let's say an epsilon of 2.5. We kind of do a search and we find some solution, and then we save that solution. And then if in between, let's say somebody queries, give me a solution, we return it. But if we have more time on our hands, we just repeat our search with a smaller epsilon value. So let's say 1.5. We find potentially a better plan. If not, then we are sure that the solution we have is kind of within a factor of 1.5 of the true optimal solution. So in this case, on the simple example, we don't actually change anything, but we needed a few more expansions because our epsilon is smaller, so it takes some time to compute this proof that there's no solution that is better. And then if we have even more computational time, we finally just set epsilon to 1.0, which is equivalent to a regular A star search. Then we need to explore way more states, as you can see here with the gray example areas. But we also find a solution that is potentially slightly shorter. So what do you think is like maybe downside of this approach for any time plan? Yes?
Because it's a real-time system, we first move the direction of the suboptimal solution by downwards. We update a lot of path later on to the optimal solution. We have to back.
Okay, that's
and follow.
That's an interesting point. So one problem is if the whole thing takes too long, so now a starting state might not even be valid anymore. So this would only work if like even the sequence of planning is so fast that we haven't even really reached that second size that you mentioned. Any other downsides that you can see maybe from an algorithmic perspective?
Maybe that we repeat computations that we already did in the past before.
Exactly. So I think in this image, you can see it quite nicely, like the cells as you expand are marked in gray, right? So the first iteration, we expand these cells. And the second iteration, we basically expand the same cells and then 2 additional ones. And then the third one, we still expand the original routines and the 2 additional ones. And then on top of it, another 5 additional ones. So it really seems like we waste a lot of our computational effort here. Okay, so answer that. So there's many states between iterations. Okay, and so there's a way to fixing that, and it is known as anytime repairing A star or ARA star. And the basic idea of ARA star is that we have to keep track now what states we have already visited. So in particular, we do not only have the original G values, but we also add another kind of lookup table for the GE values, which is kind of the G values when we last expanded that particular vertex. And between high-level iterations, we need additional memory to just store this lookup table or these GE values. And then whenever we start our A star search, we basically do not only add the start state in our open list, but we add all the states that fulfill this condition in our open list. And then at execution time, we just execute a weighted A star, and we even have an additional termination condition that says if the F value of our goal node is greater than the, again, like the smallest F value that we have in our open list, then we don't even have to continue searching. And on the examples that we have just seen before, that has kind of the advantage that we don't need many more expansions. So when we go from 2.5 to 1.5, instead of expanding now as before 15 cells, we only need one additional expansion. And then if we expand, if we change our epsilon to 1.0, we just need 9 additional expansions, and we find the better solution. So this was very quick, but there will be an exercise where you can basically try running the anytime repairing and comparing it to just a sequence of focus searches on the exact same like examples that we had in the lecture. And so you can play a little bit with like understanding this GE data structure and also with how much you can save by doing. Do you have any questions? Any questions regarding any time plan? Okay, then the last extension we want to discuss is known as incremental planning. And the incremental planning now deals with the fact that the graph might change. For example, while we execute, like let's say we started executing and then we notice an edge is missing. So instead of really starting to a search from scratch in the new graph, it would be really nice if we could just reuse as much as possible from our previous search effort, just remove this edge and then redo whatever we need to redo. And that's exactly what incremental planning is. So it is the reuse of the previous search result, and it typically only makes sense if you also put it in an execution framework, meaning you interleave planning and execution in some way. And so we don't really go into details in the lecture here because it's all still past planning, not so much on robot specifics. But I want to point out 2 like state-of-the-art algorithms, and you will have the references in the slides. So the first one is known as D-star light, and it also keeps track of these G values from when they were expanded between iterations. And then it just has some new additional special mode that happens when an edge cost increases. And you can see an edge being removed also as an edge cost increase, because then the edge is basically the cost is infinite. Okay, and then the second one that I also just want to basically mention by name is called Anytime D-star. And that is basically a combination of this anytime repairing A-star and the D-star light algorithm. And you can find the paper with like the details on the pseudocode in the reference. Okay, any questions regarding A-star or A-star extensions? Perfect. Then let's talk more about robots. Okay, so we want to apply this sort of idea of search-based planning to real robots. And here's again one example that you think I've also seen in the last lecture, where we have a car-like robot, and we want to use search-based planning to plan for this sort of robots that does not operate in a grid-like environment. And the idea here is to use something that is known as a state lattice, where you have as edges motion primitives, and you can use these motion primitives and replicate them many different times in order to generate a lattice graph. Why is it called a lattice? Because we assume that we start as kind of fixed lattice or grid positions for the motion primitives. So for example, this one is at 0, 0, and then we can go to 8, 8, for example. And if we make sure that all the motion primitives very neatly align in this lattice-like structure, then we can very easily reuse even these only 5 primitives we have to build very large search graphs. Okay, and so before we kind of more formally define what motion primitives are and also discuss where they come from or should come from, let's see first how this sort of planning would affect A star. And so on the left-hand side, I have, again, the A star vanilla algorithm, similar to, or like a slightly modified version to what you have seen in the last lecture. So we have our open set, which is a priority queue, that we start with our start vertex. Then in the iteration, we repeat until our open list is non-empty. We take the smallest value based on the F value. If that turns out to be the goals, and we return the solution. Otherwise, we have our expand operation, which goes over all neighbors. And then we compute this intermediate G value. And if there's an improvement, so we found a better cost, and then we insert it or update like the entry in our open priority. So which of the parts in this pseudocode are basically now critical or maybe need some changes in practice to make it work for state lattices? Like one way to think about it is, imagine you would need to implement it. Last exercise, you might have tried to implement regular A star. Now imagine I would give you 3 motion primitives. What would you need to change in your implementation such that it would work?
Yes, how the neighbors are implemented.
Exactly. Like before, it was maybe just like an 8 connected grid or 4 connected grid where we could hard code what the potential neighbors are. That is going to be tricky now. Anything else? Okay, then I think that's mostly it. And so before I kind of formally define how we can update the neighbors, let's now look at what a motion primitive actually is, because then we can also define how the neighbors should look like. So intuitively, a motion primitive is just a short, valid trajectory that obeys robot dynamics. And so you might have heard this like thing before. And it actually turns out that it's very similar to what we did in the very first section. So formally, a motion primitive is a tuple of 3 entries. So the first one is the duration. The second one is some sequence of control actions. And the third one is some sequence of states. And we wanted such that the sequence of control actions and states follow our dynamics equation over the whole duration of the motion primitive. And that also means that the motion primitive is specific to some sort of robot type, because the robot type defines our dynamics. And so this, in principle, is extremely similar to the definition of kinodynamic motion planning from lecture 1. The only kind of difference now is that we do not have a cost function here, and we also don't have these like collision constraints. So typically, motion primitives you completely ignore the collision constraints because that you want to look at runtime. The cost function you sometimes include. Like often it's not formally included, but when you generate motion primitives, you're obviously not interested in weird circle-like motions, but maybe like the shortest possible motions or the fastest possible motions. So often you have some J that you also try to minimize. Okay, and then what do? So as I said, you have to discretize your configuration space using some sort of lattice. So here's one example with a car. We create this like grid-like structure for the different positions. And we also say that the car can be oriented like at different angles. So in this particular case, as X and Y are kind of in a grid-like structure, and theta just has 4 options, like forward, left, right, and backwards. And then here we have kind of, in this example, 6 motion primitives, which means the car can always go straight forward or straight backwards, or it can do kind of a left turn and a right turn. Every time it does a left turn or a right turn, it will also change the theta angle of the configuration to fall exactly again in the grid. And then if you want to kind of search in your graph, then you can now, because you're in this lattice, you can construct this graph and repeat as the same sort of motion primitives. And if you do it kind of a lot of times, you get this very dense graphs. Okay, and that basically means that for the state lattice motion primitives, we have additional constraints. So in particular, we define a subset of our configuration space that is discretized. And then we need constraints that the first configuration is really an element in this discretized configuration space. And the same holds true for the last element. Okay, and now we can go back to kind of the neighbor computation. And we can state that neighbor becomes a neighbor if basically the start state matches to the state we have for the vertex. And the resulting motion also needs to be collision free, because we now might have obstacles in our workspace. And of course, we do not want to include neighbors that result in any collisions. And yeah, so motion primitives are usually pre-computed. We do it once for a kind of robot. Then when we want to find a neighbor, all we need to really do is, because we have to verify this condition, is that we put all the motion primitives, for example, in a hash map that uses as key the initial state, Q of 0. And then we can just look up this hash map in like constant time, what are the suitable motion primitives that we can expand. And then for all suitable motion primitives, we will check if the motion is collision free. Okay, so that leaves us with the problem on how can we do efficient collision checking. And there's in principle 2 options. So the first option is known as a swept volume, where we compute the actual volume that the robot will occupy while like traversing our motion primitive. So here's a little example. We have a kind of very long car or rod-like robot that moves on this like 90-degree rotation. And what we can do is we can discretize that motion at very fine places, and then kind of takes a union of all these different shapes. And if you do that, this collision shape looks like that. Now you might note that this collision shape is unfortunately not convex, it's concave, because if you take any 2 points, like for example this point and that point, then the line between the 2 points does not lie inside that collision shape. And so that's not so great for collision checking because it's going to be slow. Now, once you have the shape, then you can check for intersections with obstacles fairly efficiently. So you just take your swept volume and all your obstacles. If that's collision free, then we're good. Now, in the flexible collision library that you have learned about already, this sort of swept volume is implemented, or it's also known as continuous collision checking, if you have seen it. One downside is that at least in FCL, it only allows linear motions. So if you traverse on a line, it can do it for you. Anything else, it doesn't support out of the box. If you want to do it yourself with the swept volumes, then it can be difficult, and it might be a concave object, which you then need to typically convexify again in order to get fast convergence. But the advantage of this method is that it's fairly accurate if you do it like that. The second option is to discretize your workspace as well. Like imagine now, instead of really just looking at a true continuous space swept volume, we now look at a discretized swept volume. So down here is an example where we have fixed kind of grid cells, and then whenever any part of the robot covers a grid cell, you mark it as an obstacle. It's a much more pessimistic approximation because, for example, this point over here is never really covered by the robot. But in practice now, you can do the collision checking very efficiently, because now all you have to do is for each motion primitive, you kind of store which of the grid cells were occupied. And you know that the motion primitive itself is always in a lattice. So the only thing you have to do when you do collision checking is to check basically a big Boolean array if there's any overlap. And in both cases, we can actually pre-compute the swept volumes as part of the motion primitive. So in principle, you can also extend this tuple of the motion primitive to not only include the sequence of U's and Q's, but also some representation of your volume that your robot occupies. Okay. Now the other change we probably need to do, and that we haven't really discussed yet, is the cost and the heuristic. So of course, in principle, for kinodynamic motion planning at least, we had this very generic J cost function, which just gets the total computed sequence of our states and actions as input. Now we do a graph search, which means we can actually only support a subset of these cost functions which are actually additive. So if you add all the different motions of your solution path, and you get for each of these individual motion a sub cost, and you add them all up. That's the kind of cost function we can support. And that's also nice because that actually means that we can pre-compute this cost and add it as part of the motion primitive. And so for example, interested in path lengths, we can always store it already as a real number. If we're interested in time, we can also store it as an additional real number as part of our motion primitive database. Okay, and then of course, we want to use A star with a non-trivial heuristic, which means a heuristic that is somewhat informed and not just report 0 for every single state in order to search very efficiently, which means the heuristic needs to be actually admissible and never overestimates the true cost. And that actually is really robot dependent, unfortunately. But here's one example. So let's assume we have this very basic minimum time cost function. So our cost for each motion primitive is just kind of the duration that the primitive takes. Or in other words, the total cost of our motion we want to minimize is the time it takes from the start to the goal. So then if we assume we have some sort of robot that is a first order model, which means we kind of control the velocity more or less directly, and we know at what speed it can, in the worst case, operate. Let's say that speed is S max. Then one example of an admissible heuristic is that we just take the Euclidean distance between our current state and the goal state, which is the distance, and divide it by the fastest possible speed of our robot. And that gives us the shortest possible time the robot could take to get to the goal. Yes, and then in the exercise, you will kind of look at second order models, like what would happen if you can not only control the velocity, but maybe you have a bound on the acceleration as well. Any question regarding the heuristics? Okay, well, I have one more thing. So the heuristics ideally kind of combine the knowledge of geometry and dynamics, right? So you need to kind of know what is the true shortest distance geometrically. And we also need to know what kind of motions can the robot do. And so for time, it was easy. For some other things like minimum energy, it can be extremely tricky, especially if you have systems that are, for example, acceleration controlled, where you might not need any energy if you don't accelerate or decelerate. So coming up with heuristics is just difficult. Okay, but that's all I wanted to say about the heuristics. And then I think the last change we typically have to do is in our A star is to change how we search the graph. So most of the times when we implement A star, at least in these kind of university assignments, is that you assume you have this underlying grid structure. And in many places in A star, you can directly make use of that, like for example, by having more efficient collision checks by knowing that you have a grid instead of a graph. And so instead, what we really have to do when we deal with motion primitives is, because the resulting real graphs can be very big, we cannot explicitly have them in memory and first construct the graph and then search the graph. Instead, we have to use this implicit graph representation that you learned about in the last lecture. So in particular, just to remind you, what you do is you have you start your graph with your start state S, then you have a successor function that basically just tells you for a given state what are the potential successes, and then you just expand your graph or add nodes to your graph and edges to your graph based on that success function. Okay. So now we have figured out how we can use A star and by extension also variants of A stars that we discussed this morning for robots if we can use the state lattices. And so the question now is, do our nice properties, which were complete, optimal, and optimal efficient, also hold for kinodynamic motion planning in this case? And that's a discussion for you where you can provide some input. And maybe we can go, I mean, you don't have to answer everything, we can go one by one. Potentially the easiest is completeness. Sure.
I think it's probably optimal and efficient for the given motion primitives, because it's obviously not gonna find the most efficient global solution for infinite motion primitives, because we just provide motion.
Exactly. And what about completeness then? So the definition of completeness was the algorithm will find a solution if one exists.
And it's probably the same for the given motion primitives. It will, if there's a solution for these motion primitives.
Yep. Perfect. And so especially people more from the discrete search community, like kind of this first interpretation, which is, yes, all the properties remain the same, and they typically term as with respect to the discretization or choice of motion primitives. And in the limit, we could use kind of infinite many motion primitives. Of course, that would mean our branching factor also becomes infinite. And then it would even hold for the continuous problem, which is impractical, but kind of nice to think. The second interpretation is because the limit case is completely impractical, the approach itself is kind of incomplete, right? We can prove that very easily by constructing an example with like motion primitives where we cannot find a solution. For example, a narrow corridor, where we have primitives that are just not are not able and going to go into the narrow corridor because of the state lattice discretization. So if you have only motion primitives that go every 8 meters, but you have a corridor that's exactly at like 4 meters, you will never be able to go through. Okay, and that brings us to the practical challenges. So how can we actually compute motion primitives? So let's first assume that we made some assumption on what our start configurations and goal configurations should be. Then the motion primitive computation is actually just a small kinodynamic motion planning problem, as we have defined in the very first lecture, with the only slight difference that we don't have any obstacles in the workspace. So the workspace is kind of empty. And so often we also call that a two-value boundary problem, or TVBP. And we can, in principle, solve it with any other kinodynamic motion planner, maybe even with switch-based with smaller primitives, but it becomes kind of like a bootstrapping issue, of course. And in practice, what most people do is they also use some sort of domain knowledge, like for example, car-like robots. It's not so difficult to just try out what kind of steering angle you would need in order to get like this perfect 90 degrees turn. Or if you don't have this particular domain knowledge, then optimization-based approaches work really well, because at the end of the day, the small kinodynamic motion planning problem is focused just on the dynamics part, not on the obstacle part. Where optimization-based approaches tend to be very effective. And we will discuss some of these approaches also in kind of the fourth part of the class later in the semester in about 5 weeks. Okay, and then the second big problem is, even if you're somehow able to compute these motion primitives, you have to decide what are good start and goal states, which typically comes down to what should be the discretization scheme for your lattice. And so often what you try to do is you want to minimize your efforts, so you try to identify symmetries and invariances. Simple example is again a car. It's actually sufficient to compute, let's say, the left turn, forward, and right turn motion once, and then you can apply it anywhere in the space. So it's translation invariant, but it's also rotation invariant, because like you can use almost the same primitives with some slight modifications if you just turn the start state of the car. And then one other approach, apart from the domain expert, would be a data-driven approach. So you can, for example, ask a human to generate some motions for driving around, and then try to identify the most commonly or reoccurring motions that you have, and use these as motion primitives. Okay, and another challenge is that the state lattices scale very poorly with the number of primitives. So we have just discussed from a theoretical side, it would be kind of nice to have more primitives, because then we get closer to the true continuous properties of completeness and optimality. But on the other side, the kind of state space that you have to explore grows exponentially with your number of primitives, and you will see some very concrete examples also in the next exercise to kind of demonstrate it. Now, the state of the art is that we can handle up to 12 dimensions fairly well with the search-based primitives, and that was, I think, kind of like a mobile robot that also has an arm. But most of these systems require fairly careful tuning and expert knowledge, and we will look at some kind of concrete examples in a little bit. Okay, any questions about state lattice search-based planning so far? Yes?
In these cases, we didn't model like the current velocity of the robot, right? So the motion primitives were all the same, no matter if the robot was moving beforehand or not.
Yes.
So does this approach work in reality well, or how? I mean, that's not how it works in reality, I guess.
Okay, so I guess I have to explain two things. So the first thing is it also applies to systems where you have different velocities. So what then happens is, for example, you have not only x and y and theta in your state space, but you have also the velocity in your state space. And then you have to discretize the velocity as well. So for example, you would say, I'm at this point and I consider maybe 0 meters per second, 1 meter per second, and 2 meters per second. Like, so you get many more combinations of things in your motion primitives. And I think in the exercise might be also an example of that. So in principle, it is applicable. So the first part of your question is it even realistic? Yes, if you include the sort of higher order states, it's realistic. Now the problem is that then you increase your dimensionality, And then you need more primitives, and then it becomes kind of less usable in practice.
Okay, so you try to ignore the velocity?
So you, in most cases, people try to make the state space as low dimensional as they can to get away with it in practice, right? So cars, for example, are often just first order models that we have discussed, because the acceleration, like if you have a very powerful engine, is so good that you can kind of ignore this limit in many cases. But it depends on your application. Any other questions? Okay, then let's look at some concrete examples. I think there's two. So the first one is quite old, but I wanted to include it because that was also like the time where I would say this method was invented or reinvented in some sense. And that was the DARPA Open Urban Challenge. That was a challenge that basically started the whole autonomous driving commercial business. So basically it was funded by the US military branch, DARPA, where there was a big competition where cars had to first drive more like in a desert-like environment, and later on this particular challenge in like a more city-like environment, fully autonomously. And the different teams had to work on like the full stack, like add the different sensors and to the state estimation and motion planning on board the cars. And it turns out that in this particular challenge in 2007, the team that invented and used search-based, lattice-based motion planning actually ended up in. Of course, not only the motion planner was as a reason for it, but it's certainly an important. And so what they did, they actually had the state space that is augmented the speed. So it's like a car-like robot, of course. So we have X, Y, and theta, and we also have the current forward speed. And that already is quite tricky. So if you have kind of a fairly dense grids, and you need 36 actions, and they kind of for each state, and they discretized the X, Y, and theta. The theta is discretized in 32 different angles. And for the speed, I haven't written it down, but presumably also at least 3 or 4 different speeds that were discretized. And so it turns out that in this particular case, it's actually too difficult to just plan on this very dense resolution lattice. So instead, they had the idea of doing a hierarchical abstraction where they combine it with a low resolution lattice. And the low resolution has the same kind of discretization in X and Y space, but it uses fewer potential headings and potentially also fewer speed settings. And then what they do is that they kind of first plan in the low resolution lattice because the branching factor is smaller, and then they can do finer planning using the dense resolution lattice. And they use anytime D-star algorithm, as that was the one that we didn't discuss in detail, but it was this combination of this ARA star algorithm that we did discuss and the incremental approach that can deal with newly appearing obstacles or changing edge base. And then, of course, all of these search-based methods are actually extremely dependent on the heuristic. So if you would use a heuristic that is just completely uninformed, so that h to 0 in all places, then the search graph becomes so big that you don't find anything. And so the heuristics they actually used is that they tried to decouple the approach in 2 different parts. So they looked at as the first part that only considers dynamic constraints, but kind of ignores the obstacles in the environment. So it doesn't have any geometric reasoning, but it knows, for example, that if I have to park and I have to do this kind of U-turns, that's really costly, right? Well, if I go at a high speed just in a forward motion, that's not very costly. And they just pre-computed that heuristic for the high resolution lattice. And then they also have a second heuristic that is just based on the geometry. And for that, they basically kind of ignore the dynamics of the car. They just put in a little grid and they run on the grid, like for kind of like a robot that moves in the grid, a regular A star is another heuristic that can compute kind of the shortest path. So for example, if you have this wall in between, then you know that this very simple heuristic of just shortest Euclidean distance bad. So you can first compute the shortest path in the Euclidean space and then use that as the minimum distance. And then both of these heuristics are basically admissible. And then to get another admissible heuristic, it takes the maximum of the two values. So they didn't find a, let's say, very smart way of combining them, but it's a way that preserves the theoretical properties. Okay, and here's a great video from 2007 on how it actually looked like. And you can see a little bit what the challenge was like. So you're in this semi-urban environment where you have houses, you have other cars that are parked. And in this particular case, I think the goal is that the car has to also park first, and it has to automatically find where a good parking spot is, and then plan the motion to get there. And so here it has, I guess, identified it. You can also see over here the different potential motion properties and how it is. What you see on the left-hand side is more like the output of the perception system based on the cameras and the LiDAR that they had on. Okay. And yes,
If I ask a question,
please.
when it approached to the car on the left side, very close, instead of it moving into the back, it made like a one whole rotation.
Yes.
And is there any specific reason that it didn't move backward, but then like rotate around?
Yeah, it seems very suboptimal, doesn't it? And
So like,
I was not involved in the work, but my personal guess is that the number of motion primitives is just not sufficient. So we're now in this very tight spot. They maybe identified an additional obstacle and had to change the plan. And they didn't have enough motion primitives to find like a solution what a human would have done, like maybe going for like just 10, 20 centimeters in reverse and then changing again. And that's exactly the problem with the resolution completeness and resolution optimality. Any other questions? Okay, then I want to show a second example. So this one is a little bit more in my domain of expertise. So it's about flying drones. And so here typically the goal is you're in a very obstacle-rich environment and you want to maybe find a valid motion that goes through a gap. And quadrotors are interesting because they are in 3D instead of 2D, of course, but they're also very agile, so they can move very quickly. And if you want to move quickly, like in principle, they could move on a straight line, but then every single time you would need to brake. So you can like move like this, brake, and move like that. But that's obviously not as efficient as if you have a smooth curve. So for time optimal quad mode of flight, you're always interested in kind of more smooth movement. And so what they actually did was, let's say, generated their motion primitives using domain knowledge. So they used some existing work on how quad motors can move on kind of polynomial-like curves, and then arbitrarily decided the discretization, and then they could compute the motion primitives in that case. And here's just kind of one example on how many primitives they have, and if you generate a real graph out of it, it becomes obviously very dense. And because it's so dense and high dimensional, they also had to use more of a hierarchical approach. And so what they did was that they first compute a solution in a very low dimensional state space. So they use this sort of first order model where you almost only reason geometrically. And then once you have that, you use it as a heuristic for your second order model, which adds some more dimensions. And so that has a downside that the heuristic is actually not necessarily admissible anymore, right? Because you plan something, but you're not, like, most cases it will actually be not a valid lower approximation. But in practice, if you don't care about this proof of bounded suboptimality, even this inadmissible heuristics can get very nice results. And so I also just wanted to kind of show that. That's a little video. So that's in a simulation environment, and you can see that it really finds fairly aggressive motions in order to go through these narrow corridors. One example. And so, to put it in perspective, the other state of the art, and the viewfinder. The other state of the art algorithms that we will spend a lot of time in is this class about sampling-based methods. If you would apply it on a full quadrotor model on a problem like this, it would be not able to find a solution at all. And so the results here are really quite stunning for the high dimensional problems. Okay, any questions about these sort of case studies? Then in the very last part of today's lecture, I want to talk about some more practical aspects of search-based planning. So search-based planning, there's a library for it, which is called SBPL, which just stands for Search-Based Planning Library. It is open source, written in C++, works on the major platforms. Its URL is given there. And it has two parts. Like, it has a bunch of these like graph search algorithms that we discussed at the very beginning of the lecture. And it also has a number of example environments already given so that we can apply it, and also some motion primitives for, I think, a unicycle, like more like a ground style robot. There's also integration with the robot operating system, or ROS, and they use as heuristics the shortest path. And the motion primitives are written in MATLAB, so not so easy to reproduce unless you have a MATLAB license. And so that I wanted to briefly show a little bit so that you get a feeling For it. Then okay, let's start with this one. Oh, that's not the one I wanted to start with. Here we go. Okay. I need my cursor. Okay, so here's just the SPPL repository as you can download it. There's a little README as well that you can read to describes how to run it. The source is very kind of easy, like the planners. You can see here it's just one CPP file for each of the planners. There's also some linguistics, and then all the environments that they have are also in a subfolder. And then they have some examples as well, and the examples are pretty. It's like a pretty simple text file format, so it tells you how many grid cells, and then it has this kind of ASCII like encoding on where's free space, which is 0, and 1 would be not free space, and where's the start and goal is. And then they have just like little test applications that you can run, and just to give you an idea on how fast it is, it just produces that, and then the solution is just in the solution file, and it really just tells you the coordinates of the verb instead. Fairly straightforward, and because it's very basic, it's actually a good resource if you want to understand some details of the algorithm, to just look at the code. And then the second example I wanted to provide is this one. That is an example that I have worked on, which really just uses SPPL, but has some more graphical utilities. And also to just give you an example, so it takes a little bit longer. And this one. And here's the example, so you kind of start at the starting state. And we have quite many motion parameters, I guess. And then the goal is to move to the other side. And that's also open source, and you can kind of look at it and play with it if you want. Okay. That's also SPPL, and I think it was ARA star. Okay. And back. So SPPL, basically what's nice is that it's really fast, as you have seen, like that was just running on my laptop. It has the implementation of these different search-based methods, and is used in other like commercial robotics places. But it is pretty difficult to define new environments and to use custom motion primitives. And right now there has been not so much changes there. Okay, and then to conclude, so today we kind of learned two big parts. The first one was we looked at more advanced techniques for a star, On one hand, we looked at anytime planning for real-time search. So in particular, we looked at weighted A star and focus search. And we also looked at incremental planning that is relevant if your environment is dynamic. And then the second big part, we looked at how can we apply now A star and its variant to kinodynamic motion planning by using state lattices. And we discussed what the theoretical guarantees are and what the state of the art is, which robotic systems could be handled, and also the difficulty with the scalability. And the next week, we actually will start with a different approach of motion planning, which is sampling-based motion planning, which we will work on for about 5 weeks. Yeah, if you want to know more, here's some suggested reading, and I'm happy to take any final questions. Okay, so thank you everyone, and see you next week.